The film opens in silence. A silence so vast it feels alive, breathing between galaxies, humming beneath the bones of existence itself. A faint light flickers, then another. Galaxies drift across the black, spirals of ghostly fire, their arms stretched like memories trying to hold on. The narrator's voice emerges, and now slow, measured and haunting. What if everything we see on every star, every planet, every breath is not the beginning, but the end? The camera glides through the cosmic ocean, through nebulae that bloom like dying embers, through clusters that shimmer with ancient exhaustion. What if the universe has already perished, and we are merely witnessing its afterglow, the stretched light of a song that has long since stopped? Every photon that reaches our eyes, every sunrise, every galaxy seen through a telescope, is history. A record of what once was. The universe does not show us the present. It never has. The cosmic microwave background, a faint radiation filling all of space, whispers across the void. It is the oldest light we can detect, the fading echo of the Big Bang itself, a fossil, glowing faintly from 13.8 billion years ago. If entropy is destiny and heat death inevitable, what if it already happened, and we simply don't know it yet? Stars collapse into silence, matter decays, time itself begins to blur, the past bleeding into the now, the future dissolving into memory, and somewhere in that stillness, the question lingers like a pulse beneath eternity. Are we living in the living universe, or inside its ghost? In the early years of the 20th century, the universe was thought to be eternal, a grand, unchanging stage upon which stars lived and died, but where the cosmos itself stood still. Albert Einstein, in crafting his general theory of relativity in 1915, glimpsed the mathematical machinery that could describe the curvature of space-time, the invisible architecture of gravity. Yet even he hesitated before its full implications. His equations, left untouched, suggested something impossible, that the universe could not remain static. It must expand or contract. Einstein resisted. He added what he called the cosmological constant, a delicate mathematical patch meant to hold the universe in place, to stop it from either collapsing or blowing apart. For in his time the stars seemed fixed, the heavens serene. To imagine them rushing away into darkness was to imagine chaos itself. But the universe was not still. It never had been. In the 1910s and 1920s, atop mountaintops crowned with new telescopes, astronomers began to read a faint and startling message hidden in starlight. Among them was Vesto Melvin Slipher, who at Lowell Observatory pointed his spectrograph at the spiral nebulae, the strange misty whirls beyond the Milky Way. What he found was unsettling. Their light was shifted, stretched toward the red end of the spectrum, a redshift. In laboratory physics, redshift meant motion. An object moving away from the observer caused its light waves to lengthen, just as the pitch of a receding train's whistle drops as it speeds away. But these were not mere stars or clouds. They were galaxies, entire island universes, and they seemed to be fleeing. By the time Edwin Hubble took up the same cosmic trail at Mount Wilson, the truth was undeniable. Using the powerful Hooker telescope, Hubble measured the distances to dozens of galaxies using Cepheid variable stars, celestial lighthouses whose rhythmic brightening and dimming revealed how far away they were. The farther the galaxy, the greater its redshift. The universe was expanding. The revelation shattered the stillness of Einstein's cosmos. Space itself was stretching, carrying galaxies apart like dust motes adrift in a rising tide. The light between them grew thin, its wavelengths drawn out by the very fabric of space-time. What had once seemed infinite and unchanging was now dynamic, alive, evolving. Einstein, upon hearing of Hubble's discovery, is said to have called his cosmological constant the greatest blunder of my life. Yet that blunder had disguised something extraordinary, that the universe had not always been as it is. If it was expanding now, then in the past it must have been smaller, denser, hotter. Rewind the cosmic clock, and everything, every star, every atom, every point of light, collapses into a single, searing instant of creation. This was the birth of the Big Bang. The idea was first proposed by Georges Lemaitre, a Belgian priest and physicist, who called it the primeval atom. To many, it sounded absurd, a universe born from nothing, erupting from a singular point into being. But mathematics, observation, and later, the faint traces of radiation itself would all converge to confirm it. And if the universe had a beginning, then perhaps inevitably, it would have an end. The decades that followed brought new eyes to the sky, and with them, a deeper echo from the past. In 1964, two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to fine-tune a radio antenna designed for satellite communication. No matter what they did, a faint hiss persisted. They cleaned the equipment, chased down every possible interference, even removed pigeon nests from the dish. But the noise would not vanish. It came from everywhere, from every direction in the sky, day and night. Unbeknownst to them, a team of astrophysicists at Princeton University, led by Robert Dick, had been searching for precisely such a signal, a relic from the universe's fiery birth. When the two groups met, the truth crystallized. That faint, persistent hiss was the afterglow of the Big Bang, the cosmic microwave background radiation. This invisible ocean of microwaves filled the cosmos, the last light of a time when the universe was just 380,000 years old, when matter cooled enough for atoms to form, and light, at last, could travel freely through space. Penzias and Wilson had accidentally tuned into the oldest broadcast in existence, a whisper from the moment creation became visible. The discovery changed everything. For the first time, humanity could see the echo of its own origin, a light that had traveled for 13.8 billion years, stretched and cooled as the universe expanded. What once burned at thousands of degrees now glowed faintly at just 2.7 Kelvin, barely above absolute zero. The cosmos, it seemed, was not only expanding, it was cooling slowly, steadily, irrevocably. Every second, the fabric of space-time stretched a little more, scattering galaxies farther apart, dimming the ancient fire that once blazed in every corner of the universe. Entropy, the gradual drift toward disorder, was not merely a law of physics. It was a prophecy. Stars burn their hydrogen into heavier elements, radiating energy into space. Eventually their fuel runs dry. They die, some quietly, some in cataclysmic bursts. But even the ashes cool, even the remnants fade. In this grand thermodynamic narrative, everything is in decline. The heat of creation disperses into the cold equilibrium of emptiness. The universe, once radiant with fire, drifts toward darkness, toward what physicists call heat death, the ultimate stillness where all motion, all temperature differences, all life cease to exist. To look at the night sky is to see a paradox, a universe ablaze with youth, and yet ancient beyond measure, a cosmos still alive with stars, yet destined for silence. And perhaps the most haunting realization is this: each photon we see, each shimmer of light from a distant galaxy, is a message sent long ago. We are never seeing things as they are, only as they were. The Andromeda galaxy, bright and vast in our telescopes, shows us light that left it over 2 million years ago. The edge of the observable universe, the faint horizon of the cosmic microwave background, shows us a scene nearly 14 billion years old. We are, in every sense, watching a film of the past, the slow playback of a universe that is already slipping away. In this light, the cosmos is not just expanding, it is aging. The wavelengths of its light stretch thinner, colder, more fragile. The energy that once burned in every particle is diffusing into the endless night. The first signs of a fading universe are already written across the heavens. They are not dramatic. They are not loud. They are the quiet, patient decay of time itself, the soft redshift of eternity, the cooling breath of a cosmos that once burned bright. And as the galaxies continue their silent retreat, as starlight continues to fade and stretch, one truth becomes impossible to ignore. The universe is not a static monument, but a living thing, born, evolving and destined, like all living things, to die. The discovery of expansion was not merely the revelation of movement, it was the first whisper of mortality, a reminder that even infinity, under the laws of physics, carries within it the seed of its own end. The cosmos, vast and eternal to the human eye, there's but a candle in the cold, and the flame, though bright, is already dimming. For much of the 20th century, physicists believed they had glimpsed the rhythm of the cosmos, a single predictable beat that began in the Big Bang and would, someday, slow to silence. The expanding universe, they reasoned, must be like a ball thrown upward, propelled outward by its initial force but gradually slowed by gravity's pull. Perhaps one day it might even fall back in on itself, collapsing into a final, catastrophic implosion known as the Big Crunch. That was the story for decades. Creation followed by contraction, fire giving way to return. A cosmic heartbeat that rose and fell under the rule of gravity. It was elegant, logical, and utterly wrong. By the late 1990s, astronomers had developed a new way to measure the universe's past and future, using type Ia supernovae, the thermonuclear deaths of white dwarf stars, as cosmic yardsticks. These explosions burn with astonishing uniformity, releasing a predictable amount of light. By comparing how bright they appear to how bright they should be, astronomers could measure their distance across the expanding cosmos with remarkable precision. Two rival teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to trace the universe's deceleration. They expected to find a slowing expansion, a universe gradually succumbing to its own gravity, perhaps halfway through its long descent toward stillness. But the light from the distant supernovae told a different story. The stars were too faint. The data made no sense at first. Fainter supernovae meant they were farther away than expected, farther than they should have been in a universe slowing down. Somehow space had stretched more than it should have. The calculations were double-checked, instruments recalibrated, distances remeasured, but the conclusion refused to change. The expansion of the universe was not decelerating. It was accelerating. The cosmos was not slowing under gravity's pull. It was speeding up, as though driven by an invisible hand. This single discovery, confirmed by both research teams in 1998, would overturn a century of cosmology. It revealed that the universe was not drifting gently toward equilibrium. It was racing toward emptiness. In every model physicists had trusted, gravity was the ultimate sculptor, the quiet force binding galaxies, stars and matter together, fighting the entropy that sought to tear them apart. But now something had begun to overpower it. Space itself, the very fabric of the universe, was expanding faster and faster. To understand how strange this is, imagine a balloon being inflated. The galaxies are like coins glued to its surface. As the balloon expands, the coins do not move on their own. The space between them simply grows. Now imagine that the balloon's expansion accelerates with every passing second, driven by some unseen, ever-growing pressure within. What could possibly cause space, nothingness itself, to expand faster over time? No known force fit the description. No known particle could explain it. Physicists called it dark energy. The name was a confession, not a definition. It meant simply, something is pushing the universe apart. And we do not know what it is. Dark energy made up nearly 70% of the cosmos, yet it was invisible, untouchable, and almost entirely theoretical. It could not be measured directly. It could not be isolated. Its only evidence was written in the accelerating redshift of distant galaxies, a signature of the universe running from itself. Einstein's long-abandoned cosmological constant suddenly returned from history's shadows. Perhaps some thought he had been right, but for the wrong reason. Maybe a constant energy of empty space, woven into the fabric of reality, was real after all. Vacuum energy, the energy of nothing. Quantum theory supports this in part. Even in perfect emptiness, the quantum vacuum seethes with ghostly fluctuations, particles appearing and vanishing in endless pairs. On average, the vacuum should contain an enormous amount of energy, a pressure that could, in principle, drive the universe's expansion. Yet when the numbers were calculated, they yielded a paradox so vast it bordered on absurdity. The predicted vacuum energy was 120, orders of magnitude larger than what astronomers observed. It was the most inaccurate prediction in the history of physics. A discrepancy so extreme it mocked comprehension. The universe, it seemed, was expanding just enough to defy both theory and expectation. The discovery of acceleration was more than a scientific shock. It was a philosophical wound. If gravity could no longer hold the cosmos together, then the long-term fate of everything, and of stars, galaxies, atoms, was far darker than anyone had imagined. In an accelerating universe, galaxies do not simply drift apart. Their separation speeds up exponentially. Over billions of years, even light will no longer bridge the growing void. The sky will empty. The nearest galaxies will fade beyond visibility. Cosmic structures, clusters, filaments, superclusters will unravel. And one day in the far future, every galaxy beyond our own local group will vanish beyond the cosmic horizon, receding faster than light itself as the fabric of space stretches to infinity. The universe will grow larger, but lonelier. To physicists, this realization was both thrilling and terrifying. For decades, cosmology had been about beginnings, the fire of creation, the first moments after the Big Bang, the birth of stars and galaxies. Now attention shifted toward endings. Dark energy forced the universe to evolve not toward balance, but toward isolation. Entropy, once thought to lead to a slow fade, would now be accelerated by expansion itself. The cosmic background radiation, already cooled to just 2.7 degrees above absolute zero, would be stretched further, its wavelengths lengthening into oblivion. The universe's glow would dim, not because it burned out, but because the light itself was pulled apart. The cosmic symphony was not merely fading, it was being silenced faster with each passing moment. Some theorists began to wonder if this accelerating expansion hinted at something even more unsettling. Perhaps dark energy is not constant, perhaps it grows. If so, there may come a time when it overwhelms every bond in existence, first galaxies, then solar systems, then atoms themselves. In this ultimate scenario, known as the Big Rip, space-time would stretch infinitely fast, tearing apart the very structure of matter. A universe racing toward emptiness could, in its final moments, shatter entirely. Others offered gentler endings, a gradual drift into heat death, where stars die quietly and black holes evaporate over unimaginable timescales. But all shared a common truth. The acceleration meant the universe would never come together again. The age of contraction, the dream of a cosmic rebirth, was gone. The universe had chosen expansion without end, and so, at the turn of the millennium, humanity stood in the shadow of a new kind of infinity, not the infinite fullness of creation, but the infinite absence that follows it. For billions of years, galaxies had been the architects of structure, gathering dust and gas into stars, stars into systems, systems into worlds. But now the architects' hands were unbound. The structures were drifting apart faster than they could be built. The same equations that once described the birth of everything now described its gradual unraveling. It was, perhaps, the most haunting discovery in modern science, that the universe, vast beyond imagination, is not only dying, it is accelerating toward its death. The expansion that shouldn't be is the one that defines everything. And in that silent acceleration, there lies an almost poetic symmetry, that creation itself carries within it the command to disperse, and that the greatest act of becoming is, inevitably, the beginning of disappearance. For centuries, humanity looked at the stars and imagined that light was truth, that to see was to know. But now, at the dawn of the 21st century, physicists realized that the visible universe, every galaxy, every planet, every atom of matter, was barely a fraction of the whole. The cosmos, it turned out, was ruled not by what could be seen, but by what could not. Dark matter, unseen yet gravitationally heavy, shaped galaxies like invisible scaffolding. And darker still, a force without mass, without color, without name, stretched the universe itself apart. This was dark energy. It made up 68% of everything. Not a field, not a particle, not radiation or matter, but an omnipresent pressure woven into the geometry of space-time itself, invisible, indifferent, yet it commanded the fate of all things. To describe this strange reality, cosmologists turned to a model, one elegant enough to explain observation and simple enough to remain predictive. They called it the LCDM model. Lambda, cold, dark matter. Lambda, the Greek letter. Once used by Einstein to describe his discarded cosmological constant, now stood for the energy of the vacuum, the quiet, relentless force driving cosmic acceleration. Cold dark matter described the unseen gravitational glue binding galaxies together. Together, these two invisible components accounted for nearly all of cosmic structure and evolution, leaving only about 5% for everything familiar, everything that shines. The LCDM model became the standard map of the cosmos, a mathematical symphony that could predict the clustering of galaxies, the ripples in the cosmic microwave background, and the accelerating pace of expansion. But beneath its precision lay an unease. It worked, yet it made no sense. For what exactly was lambda? Why did the vacuum, the emptiness between galaxies, have energy at all? In quantum theory, emptiness is never truly empty. Even when all particles are removed, when every field is stripped bare, the quantum vacuum still hums with activity, a restless sea of virtual particles flickering in and out of existence. These fluctuations are not fiction. They have measurable consequences. They give rise to the Casimir effect, subtly pulling two uncharged metal plates together in a vacuum. They influence the lifetimes of atoms and the decay of subatomic particles. It is as if the void itself breathes, quietly, invisibly, beneath all things. This vacuum energy, when added up across the entire universe, could act like a pressure pushing outward, inflating the fabric of space-time. But as theorists calculated the energy density of the quantum vacuum, their equations exploded into absurdity, predicting a force so enormous that it should have torn the universe apart long before stars could form. Yet the real cosmos was calm, delicate, balanced on a razor's edge. Why was the vacuum energy so small, and yet not zero? This was not merely a mathematical problem, it was a riddle of existence itself. In this unseen balance between expansion and gravity, some began to sense a deeper story. Dark energy, the silent architect, seemed to be more than a physical force. It was a kind of cosmic entropy, a symptom of the universe's slow unraveling. Every moment, the vacuum expands a little more. Every second, galaxies drift farther apart. Even as new stars ignite in local bursts of brilliance, the background energy of the cosmos continues to rise, thin, featureless, unrelenting. Perhaps this vacuum hum, the soft, omnipresent pulse of dark energy, is not the song of creation, but the whisper of decay. The sigh of a universe gently dissolving into stillness. Time too is drawn into this mystery. Einstein taught that time is not absolute. It bends and stretches with gravity and speed. Near a massive body, time slows. At the edge of a black hole, it almost stops. Relativity revealed that the now experienced by one observer may not exist for another. That simultaneity itself is an illusion. In this strange geometry, past and future are not separate places. They coexist, interwoven into the four-dimensional fabric of space-time. What we perceive as the flow of time, from before to after, may be nothing more than our consciousness sliding across this frozen structure, one frame at a time, like a needle tracing the grooves of a cosmic record already complete. And yet, if the universe's expansion accelerates, the very structure of space-time changes. Distances grow not just between galaxies, but between moments. The tempo of the cosmic clock stretches. Physicists have long known that expansion affects the frequency of light, redshifting it, diluting its energy. But what if it also stretches the perception of now itself? If time and space are two faces of the same fabric, then as one stretches, so must the other. Perhaps the universe we perceive, the glowing cosmos filled with stars, is not the living present, but the residue of an earlier state. A temporal echo, a playback of an event already concluded. The cosmic microwave background, that faint radiation from the young universe, is one such echo. It carries the imprint of matter as it once was, frozen in the geometry of space when the cosmos was still opaque. But what if the echo runs deeper, not just through radiation but through time itself? If entropy defines direction, if every action drifts toward equilibrium, then perhaps time too is not a river flowing forward, but a wave decaying, losing coherence as it spreads. From our perspective within that wave, we might mistake the fading resonance for the real thing. Just as one might hear a bell's dying tone and imagine the bell still ringing. Could the universe be such an echo? A vast resonance of an earlier, hotter, more ordered state, its music stretched across eons until only silence remains? Quantum physics hints at such possibilities. In certain interpretations, such as the Wheeler-DeWitt equation, time does not appear at all. The fundamental laws of the universe are timeless. Change emerges only as a property of relationships between states. To the universe as a whole, there may be no past or future, only configuration, only geometry. If this is true, then our perception of a flowing present is not reality but perspective, a local illusion experienced by observers caught in motion. And if dark energy is reshaping space-time itself, perhaps that motion is already lagging behind reality. Perhaps the true universe, the one beyond our horizon, has already reached thermal equilibrium, its expansion complete, its temperature uniform, and we, still watching its ancient light, still measuring its stretch, are living inside its afterimage. In that light, the LCDM model becomes more than a framework of physics. It becomes a tombstone, a precise inscription of how the cosmos fades. The cold, dark matter builds the structure. Dark energy tears it apart. The two together describe a grand cycle of creation and dissolution, a dance between gravity's embrace and vacuum's repulsion. But the deeper question remains untouched. Is the universe truly expanding? Or are we merely witnessing the stretching shadow of time itself, replaying the collapse of a greater reality that has already gone still? Dark energy, quantum vacuum, time dilation. They are words, equations, approximations, humanity's fragile attempt to describe what may be beyond description. And yet, in the silence between galaxies, in the emptiness where light grows thin, one can almost feel their presence, the faint vibration of a universe both alive and dying. Perhaps this is what the cosmos truly is. Not an explosion expanding outward through space, but a resonance fading inward through time, a memory of light still echoing through eternity. There will come a time, long after the last human thought has flickered and gone, when the stars themselves begin to die. Not all at once, but quietly, in an order written by thermodynamics and sealed in the mathematics of entropy. For entropy is not chaos. It is the slow settling of the universe into stillness, the inevitable drift toward uniformity, where energy spreads evenly, and no structure remains to do work, to think, to burn. In this final act of cosmic history, creation itself turns inward, consumed by its own perfection. First the stars. They are born in clouds of gas, live by fusing hydrogen into helium, and die when that fuel is gone. Massive stars end in spectacular detonations, scattering heavy elements into space. Smaller ones, red dwarfs, the most numerous of all, simply fade into dark, cold embers. Over the next 100 trillion years, the sky will dim as the last of these slow-burning stars exhaust their fuel. The Milky Way, once ablaze with light, will become a field of dying coals. Galaxies will fade to infrared whispers. Stellar remnants, white dwarfs, neutron stars, black holes, will orbit one another in silence. The cosmic night will deepen. Then the galaxies themselves will dissolve. Gravitational interactions will fling stars into the intergalactic dark, and supermassive black holes will swallow the rest. What remains of structure will fall toward those dark centers, merging into singularities, where gravity crushes space and time into one. Yet even these titans are not eternal. Through a process known as Hawking radiation, black holes slowly leak energy, quantum particles escaping the horizon that once trapped them. Over unimaginable spans of time, 100 years or more, even the greatest black holes will evaporate into a final whisper of radiation, leaving nothing behind but empty space. After that, matter itself begins to fail. Protons, the building blocks of atoms, are not perfectly stable. If certain grand unified theories are correct, they will eventually decay into lighter particles, positrons, neutrinos, and photons. The solid universe will dissolve into radiation until not even the memory of atoms remains. At last, only a thin sea of photons, electrons, and neutrinos will drift through the dark. Temperatures will approach the cosmic absolute, not quite zero, but close enough that motion itself loses meaning. No structure, no difference. No time. This is the heat death, the ultimate equilibrium. A cosmos where entropy has reached its maximum, where everything that can happen has already happened, and nothing new will ever occur. It is not fire that ends the universe, but silence. For decades, this has been the accepted destiny, a future written not in myth but in mathematics. Yet behind this vision of extinction lies a deeper, more disturbing possibility. What if that future is not billions of years away? What if it already exists? What if everything we see, every star, every atom, every moment of consciousness, is not leading toward heat death, but emerging from it? In the late 19th century, the Austrian physicist Ludwig Boltzmann gave the world its first statistical view of the universe. He understood entropy not as disorder, but as probability, as the number of ways a system can be arranged without changing its overall energy. In a perfectly stable, high-entropy universe, one where everything is uniform, there are no gradients, no events. But randomness never stops. Even in equilibrium, tiny fluctuations can occur. And given infinite time, one fluctuation, by pure chance, might momentarily form a pocket of low entropy, a fleeting island of order in an ocean of nothing. This is the concept of the Boltzmann universe, or, more precisely, the Boltzmann fluctuation. In such a framework, what we call the universe could simply be one such fluctuation, a brief statistical anomaly rising out of eternal stillness, experiencing itself as real before dissolving again into equilibrium. The implications are staggering. If this were true, the entire observable cosmos, its galaxies, stars, and even the laws of physics as we know them, would not be fundamental. They would be temporary illusions born from random quantum noise. The universe in this picture is not becoming cold. It already is cold. We are simply existing within a localized fluctuation, a mirage of structure, inside the already dead sea of thermal stillness. In that sense, every sunrise, every heartbeat, every thought could be nothing more than the ghostly echo of entropy, briefly pretending to be life. This idea is not mere philosophy. It grows from physics itself. According to statistical mechanics, fluctuations of any scale are possible, though improbable. The larger the fluctuation, the more complex the structure, the rarer it becomes. A single self-aware observer could, in theory, arise by pure chance formed from a random arrangement of particles within a thermal bath. Such an entity has a name, the Boltzmann brain, a consciousness without history, floating briefly in the void before dissolving. In an infinite, eternal universe, the probability of such minds arising would exceed the probability of an entire structured universe like ours emerging. If so, then statistically, you, or what you believe yourself to be, are more likely a fluctuation than a product of cosmic evolution. The cosmos, in this light, becomes a theater of illusions, a tapestry of fleeting coherence against the endless hum of equilibrium. But what if this illusion extends beyond matter, beyond perception, into time itself? If entropy is the true arrow of time, then a fluctuation that creates order might also generate the illusion of a past, a memory of causality that never actually occurred. Our histories, Our records, our fossils and starlight, all could be artifacts within the fluctuation, consistent with one another, yet without any true origin. Like a dream that seems ancient and real, but ends when the dreamer wakes. If this is so, then what we call the present universe is not a step in a grand timeline, but a singular statistical hiccup within eternity, a ghost of reality rising from the ashes of an already complete cosmos. Still, one might ask, if this is an illusion, why does it feel so coherent, so stable? The answer lies in perspective. For a being within a fluctuation, reality would appear smooth, consistent, governed by physical laws, because those very laws are part of the pattern that defines the fluctuation. From within, it all feels real. From beyond, it is merely a pattern of chance, a temporary alignment of energy in a field of perfect stillness, like frost patterns forming on glass. Intricate, breathtaking, yet destined to vanish with the next breath of warmth, and so the paradox deepens. We believe we are moving toward entropy, yet entropy may already have claimed us. We imagine the future as something that will be, when perhaps it has already ended. If time is not truly linear, if it loops, folds, or exists only as geometry, then the arrow we follow may simply be a direction within a larger motionless whole. In that whole there is no before or after, only different configurations of energy, one of which happens to resemble the thing we call life. In that sense, the vanishing future is not coming. It is already here. We are inside it, living within the echo of a universe that has already fallen silent, every galaxy a memory, every atom a remnant, every thought a flicker of improbable order arising, briefly in the dark. Perhaps the cosmos did not end. Perhaps it ended long ago. And what we experience now is the faint shimmer of its decay, a ghostly afterimage painted across the infinite void. A universe not dying, but remembering itself. The universe, it seems, may not be what it appears to be. Its stars may not burn in the present. Its galaxies may not still exist. And what our eyes perceive as life, as structure, as time unfolding, may be nothing more than the lingering light of something long dead. Yet across the silence, across the cold and ancient radiation that fills all space, theories arise, attempts not to solve the mystery but to give it form. Each is a vision of what the universe might truly be when stripped of illusion. Each is a ghost story told by physics. The Boltzmann brain, a thought in the dark in the late 1800s, Ludwig Boltzmann sought to explain entropy, the universe's relentless drift toward disorder, not as fate, but as probability. He imagined the cosmos as a vast statistical sea, where every possible arrangement of matter and energy might eventually appear, given enough time. In such a sea, even in total equilibrium, there would still be fluctuations. Tiny islands of order rising briefly from the eternal calm. A random swirl of atoms might by sheer chance assemble a molecule, a planet, or even a mind. From this logic came a haunting consequence, the Boltzmann brain hypothesis. If entropy reigns, then it is far more likely that one single consciousness could spontaneously form within the void than that an entire structured universe like ours could arise. A solitary awareness, flickering to life in the darkness, filled with memories of a world that never existed, believing it has lived, that it has seen stars and oceans and love, and then, before realizing its nature, it dissolves again into nothing. This idea, horrifying and strangely beautiful, forces a question with no comfortable answer. What if reality itself, everything seen, remembered and felt, is not the product of cosmic history, but a fleeting hallucination of entropy? A single thought echoing through a dead universe. False vacuum decay. The fragile fabric of reality, modern particle physics suggests that even the vacuum, the emptiest space imaginable, is not truly stable. It hums with quantum fields, invisible energies whose values determine the properties of everything. Matter, light, even time itself. But some theories, drawn from the Standard Model and quantum field theory, whisper that our universe might be living in a false vacuum, a temporary metastable state. Like a ball resting in a shallow valley, stable enough for now, but not the lowest possible energy. If the universe ever transitions to that deeper state, the true vacuum, the consequences would be instantaneous and absolute. A bubble of this new vacuum could appear anywhere, triggered by a quantum fluctuation or high-energy event, expanding at nearly the speed of light. Within that bubble, the laws of physics would change, atoms would collapse, chemistry would cease, and space-time itself would be rewritten. The bubble would swallow everything, and we would never see it coming. Some physicists suggest that this collapse has not yet occurred. Others speculate that perhaps it already has, and we, bound by the flow of time within our bubble, have not yet caught up to the moment of annihilation. From a higher dimensional perspective, there may be no distinction between before and after the collapse. The universe's life and death could be simultaneous, two faces of the same cosmic event, frozen into a single eternal moment. In this vision, our universe is not a living world awaiting its end. It is a shimmering ghost, the flicker of a bubble that has already burst quantum timelessness, the illusion of flow. To understand the universe's death, one must first question its most fundamental premise, time. In quantum mechanics, the equations that govern reality do not depend on time's direction. They describe a universe where every possible state exists simultaneously, where the past and future are woven together, not divided. The Wheeler-DeWitt equation, one of quantum gravity's great enigmas, contains no term for time at all. It suggests that the universe in its most fundamental form does not evolve. It simply is. Her frozen geometry of all possible configurations, eternal, unchanging, complete. In such a cosmos, the flow of time, the sensation of before and after, is not a feature of reality, but of perception. Like a projector casting one frame after another, consciousness moves through a static universe, creating the illusion of motion and change. What if, then, we are not watching the universe progress toward death, but merely inhabiting one still frame of an already completed whole? What if the Big Bang and the heat death coexist, not in sequence but side by side within the same timeless structure? From this perspective, the universe has no birth, no future, no decay, only an eternal present in which all things exist simultaneously, layered upon one another like pages in a single infinite book. And perhaps beyond our perception, the story has already ended, even as we continue to read it. The multiverse, infinite mirrors of creation. If our universe can be born, live and die what lies beyond its boundaries. Modern cosmology, particularly through the mathematics of inflationary theory, offers one extraordinary answer: the multiverse. After the Big Bang, the universe underwent a moment of exponential expansion known as inflation. But this process may not have stopped everywhere. Some regions of space could have continued inflating, spawning new bubble universes with their own laws of physics, constants and dimensions. Each universe, in this vast cosmic foam, might live its own separate life, expanding, evolving and fading into silence. Some would collapse in moments. Others might burn for trillions of years. In this endless landscape, our universe may already be a fossil, its light still traveling through higher dimensional space, even as it no longer exists in any active sense. Just as a distant star can die while its light continues to reach our eyes, the universe itself might have perished, yet still cast its radiance across the multiverse. We could be observing the afterimage of creation, the cosmic equivalent of a star's final glimmer, frozen into space-time. In this view, existence is not a single thread but an ocean, infinite worlds, infinite endings, infinite rebirths, and our own cosmos, though already extinguished, still glows faintly among them, like a candle that refuses to be forgotten. Eternal inflation, the universe that never dies. If inflation never ends, then creation never ceases. This is the theory of eternal inflation, where the universe forever births new universes, bubbles budding endlessly from the quantum vacuum, expanding into infinity. Each new bubble may inherit different physical laws, different forms of matter and energy. Most fade almost instantly. Others ignite into vast galaxies and civilizations. In this infinite process, no single universe holds permanence or privilege. All are temporary ripples in the endless expansion, momentary flashes of order in the sea of chaos. Ours may already have completed its cycle. Perhaps to an observer outside of time, it has long faded from existence, its galaxies stretched into oblivion, while new universes continue to bloom elsewhere, beyond our comprehension. In this eternal creation, there is no end of the universe, only transformation. Only the endless reshaping of the same underlying quantum field, forever birthing, forever dissolving. We may not live in the living universe at all, but in its reflection, a preserved fossil of one among countless worlds, glowing faintly in the dark ocean of infinity. The end that is the beginning. Einstein once wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. His theory of relativity showed that all events, birth, death, and every moment between, coexist in the same four-dimensional fabric of space-time. To a being beyond that fabric, there would be no sequence, no progression. The Big Bang and the heat death would not follow one another. They would simply be eternally intertwined. From such a vantage, the universe's end and its beginning are the same event, seen from different coordinates. The expansion and the collapse are not opposites, but mirror images, folded together in the timeless geometry of existence. If so, then the cosmos is neither alive nor dead. It is complete, a single unbroken structure where all possibilities coexist forever. Perhaps the universe never truly began. Perhaps it never truly ends. It simply is, a timeless monument of being, echoing across the infinite void, and we, the observers, are the ghosts, wandering through its eternal corridors, reading the story of creation long after the book has already closed. In the quiet halls of observatories and laboratories scattered across the world, a new kind of listening has begun. Not with ears, but with instruments, machines built to hear the soft hum of the dying cosmos. Each one tuned not to the noise of the present, but to the faint afterglow of eternity itself. Humanity, still standing on its small blue world, has begun to measure the end. For decades, astronomers have gazed into the night and seen the same story written in starlight. Galaxies rushing apart, light stretched and reddened by the expanding fabric of space. But expansion alone is not the mystery. It is the acceleration, the inexplicable, ever faster stretching of the universe that continues to haunt science. To understand this acceleration is to glimpse the universe's destiny. Will it expand forever, freezing into silence? Will gravity someday reverse the flow, pulling it all back together? Or are we even now watching the final flicker of a cosmos already gone cold? Around this question, the tools of modern cosmology have been assembled. A symphony of telescopes, detectors, and satellites designed to listen to the last whispers of the universe. The James Webb Space Telescope, eyes to the beginning, launched into the cold void beyond the moon's shadow. The James Webb Space Telescope peers back in time, to the era when the first galaxies ignited in darkness. Its mirrors, polished to atomic precision, capture light that has traveled for more than 13 billion years, revealing the universe as it was when it was still young and dense. But Webb's mission extends far beyond the search for ancient stars. By studying how those earliest galaxies formed, clustered, and drifted apart, Webb is tracing the fingerprints of dark energy itself, the unseen hand that shapes the expansion of space. Each image Webb sends home is more than a glimpse of beauty. It is a data point in a cosmic autopsy. By comparing the brightness and redshift of these primordial galaxies, astronomers can measure how fast the universe expanded then, and how that rate differs now. If the expansion is accelerating faster than predicted, it could mean that dark energy is growing stronger, that space itself is pushing outward with increasing force. In that case, the end may not be a slow fade, but a race toward a final dissolution, the so-called Big Rip, where even atoms are torn apart by expansion. And so Webb listens, not for sound, but for silence, for the subtle distortions in the ancient light that whisper of a universe losing its balance. One faint photon at a time, Euclid and Desi, cartographers of the invisible. If Webb looks backward in time, the Euclid mission and the dark energy spectroscopic instrument, Desi, look outward, mapping the cosmic present with exquisite precision. Launched by the European Space Agency, Euclid is designed to chart the distribution of billions of galaxies across more than a third of the sky. By measuring how these galaxies cluster and how their light is bent by gravity, a phenomenon called weak gravitational lensing, Euclid reveals how matter, both visible and dark, weaves the cosmic web. The shape of that web carries a secret, how dark energy has stretched space over billions of years. Every distortion, every subtle pattern in the arrangement of galaxies becomes a record of cosmic evolution, a history of expansion written in the geometry of the universe itself. Meanwhile, DSI, stationed at Kitt Peak in Arizona, measures the redshift of over 40 million galaxies and quasars. Its mission is to build the largest 3D map of the cosmos ever created, a dynamic portrait of how structure has changed with time. Together, Euclid and Desi form a pair of cosmic cartographers, mapping the invisible architecture of fate. Their combined data will test the very nature of dark energy. Is it constant, as Einstein's cosmological constant suggests, a fixed property of space-time itself? Or is it evolving, growing stronger or weaker as the universe ages? The answer could decide everything, whether the cosmos will expand eternally into an icy stillness, or slow and collapse into fire. CMB Stage 4, the oldest light if the night sky is a cathedral. The cosmic microwave background at the CMB is its lingering song. This faint radiation, discovered by Penzias and Wilson in 1965, is the oldest light in existence, the afterglow of the Big Bang itself, still echoing through space at a temperature just above absolute zero. Now, decades later, scientists are preparing to listen to it again with unprecedented precision. The CMB Stage 4 experiment, a network of telescopes in Chile and Antarctica, will measure the tiniest fluctuations in that ancient light. These fluctuations, mere millionths of a degree, record how matter was distributed when the universe was young, but they also reveal how that distribution has changed, how the expansion of space has stretched and cooled the CMB over time. By studying these subtle distortions, cosmologists can test whether the expansion rate, known as the Hubble constant, has been steady, or whether it has changed in ways that point to evolving dark energy. Already, a tension exists. The expansion rate measured from the early universe does not perfectly match the one observed today. This discrepancy, known as the Hubble tension, may be a statistical quirk, or it may be the first sign that our understanding of cosmic time itself is incomplete. CMB S4 will listen for the truth in the faintest whispers of ancient light. Because if even those photons begin to fade differently than expected, it might mean the universe is entering its final phase, cooling faster, dimming faster, vanishing faster than our models predict. Gravitational waves in the universe trembles while telescopes watch light. Another kind of instrument listens for something older, deeper, the ripples of space-time itself. Gravitational wave detectors like LIGO, Virgo, and the upcoming LISA mission detect the tremors left by colliding black holes and merging neutron stars and cataclysms that warp the fabric of the cosmos. Each wave carries information about gravity's behavior across billions of light years. And by studying how these waves propagate, how their strength fades, how their frequencies stretch, scientists can test whether space-time itself is changing. In the far future, if dark energy continues to accelerate expansion, even gravitational waves will lose their coherence. Their wavelengths will stretch beyond detection, their signals drowned in the vacuum's hiss. But for now they reach us, faint, rhythmic echoes of a universe still trembling, still alive. Together with electromagnetic observations, they form a new language, a way to test whether cosmic structure is growing or dissolving, whether the gravitational constant remains constant, or whether it too is slipping away. Each detection, each whisper of merging black holes, is both an act of observation and a countdown, a measure of how long the universe will continue to sing before it falls entirely silent. The question at the edge all these instruments, Webb, Euclid, DC, the CMB experiments, the gravitational wave observatories, are listening for the same thing, the future of the universe. They are searching for evidence of what cannot yet be seen, the invisible handwriting of fate, traced in photons and gravity across the void. They are measuring not only how the cosmos behaves, but how it ends. The question that drives them is both simple and unanswerable. Is the expansion accelerating forever? Or will it one day stop, perhaps even reverse, collapsing into itself or fading into nothing at all? The data grow more precise, yet the mystery only deepens. Some scientists suspect the acceleration may be slowing, hinting at an eventual balance between expansion and gravity. Others see signs of an even darker truth, that the universe is already in its final stretch, its expansion so advanced that what we see now is merely its ghost. Perhaps, then, all these telescopes and detectors are not peering forward in time, but backward. Perhaps the light they gather, from ancient galaxies, from primordial radiation, from the shivering fabric of space-time, is not the promise of what's to come, but the echo of what has already passed, the universe cooling, the galaxies dimming, the stars long dead, their light still arriving, like messages from a civilization that has ceased to exist. In this way, cosmology becomes an act of mourning as much as discovery, a slow, patient listening to the echoes of creation's final note. The James Webb, Euclid, DESI, CMB-S4, LIGO, they are not merely instruments of observation, they are instruments of elegy, listening to the dying pulse of the universe, trying to understand what it means that we can still see its light after the fire has gone out. Silence. Not the silence of absence, but of completion, a silence that follows after everything has been said, after every light has burned, after every equation has reached its final sum. In that silence, the universe lingers. Its light still crosses the void, its galaxies still shimmer in our telescopes, its story still unfolds in our minds. And yet beneath it all, one question hums quietly, endlessly. What if this, all of it, is already over? If the universe has already ended? If everything we see is only the stretched and fading echo of what once was, then existence becomes something stranger than survival. It becomes memory. A remembrance written in photons, preserved in the geometry of space-time. Every star we see has already died in some measure. Every beam of light we catch has traveled across distances so vast that the object which cast it may no longer exist. The sky, then, is not a view of the present, but a map of ghosts. Perhaps the entire cosmos is such a map, an ancient radiance still flickering through the void, unaware that its source has long since vanished. We, the observers, are part of that radiance, particles arranged by chance and law into a temporary pattern capable of reflection. And through us, the universe remembers itself. In this light, consciousness is not an accident of biology. It is a defiance, a fragile spark in the wind of entropy. For all the universe's laws bend toward stillness, consciousness moves against that tide. It gathers orders, connects. It recalls. Every thought, every act of awareness, every glimpse of beauty, all are reversals of the cosmic drift toward equilibrium. Like tiny eddies in a river of dissolution, we hold form for a while, reshaping chaos into meaning. And though brief, that act of resistance is profound. The second law of thermodynamics dictates that disorder always increases. And yet here, within that law, something has arisen that can know it, that can look upon the decay of stars and call it beautiful. Perhaps that is what consciousness is. The universe, briefly awake, witnessing its own fading and finding grace in it. If the universe is already dead, if we live inside its cooling ashes, then our existence does not become meaningless. It becomes miraculous, a final flicker of awareness in a cosmos grown cold. A last song sung to itself before the quiet. Our galaxies, our atoms, our minds, all are echoes within the afterimage, and yet the echo shines. It shines in every act of creation, every gesture of love, every question that asks, why does anything exist at all? For even if this is a simulation of memory, a resonance of a world that has ended, the awareness of that memory gives it life again. To remember is to resurrect, if only for a moment. And we, all of us, are that moment. There is an ancient symmetry between the cosmos and the human heart. Both burn for a while, both transform, give heat, give light, and then fade. Yet even after death, their light travels on. When a star collapses, its photons continue their journey through space for billions of years. They outlive their source, crossing distances so vast that to any who might see them, the star still shines. In that sense, nothing truly vanishes. It only changes form, changes tense. Human lives are the same. Each thought, each kindness, each act of creation sends ripples into time that do not stop when the body does. Like starlight, we radiate into the darkness, carrying our imprint into futures that will never know our names. Perhaps this is what the universe has always done, radiating, remembering, reliving itself through what remains. To live inside a dead universe is to live inside its memory, and memory, by its nature, is never static. It moves, it echoes, it breathes through recollection. Perhaps what we call time is not a river flowing forward, but the pulse of remembrance itself, the universe recalling its own existence one moment at a time. And we, within it, are the neurons of that cosmic mind, sparks of temporary awareness firing within a grand ancient skull made of space and dust. Our lives may be brief, but in the act of observation, we grant the universe continuity. We complete the circuit between what was and what is remembered. The cosmos, through us, looks back upon itself, and in that gaze, becomes whole once more. From the first light of the Big Bang to the faint radiation that still whispers across the sky, the universe has always been a dialogue between creation and decay, between the moment something becomes and the moment it begins to vanish. Maybe the two were never separate. Maybe the birth of the universe and its death are the same event, seen from different angles. A single eternal act, the cosmos inhaling and exhaling itself. And within that breath, for the briefest instant, consciousness flickers awake, to feel, to see, to ask, to remember. If so, then the meaning of life is not found in escaping entropy, but in illuminating it, not in lasting forever, but in shining while we can, in adding our own radiance to the afterglow of a universe that once was and perhaps still is, in some timeless sense. Every heartbeat, every idea, every moment of love or wonder becomes an act of cosmic grace, a reaffirmation that even as the universe cools, something within it continues to burn. We are, each of us, the dying embers of stars, carrying forward the fire that once filled the heavens. And though that fire may fade, it leaves behind warmth in its memory. In art, in science, in the faint persistence of curiosity, the universe may be over, but its echo is not. It reverberates through us, through the atoms of our bodies, through the questions we ask, through the act of wondering what it all means. Perhaps that is the final purpose of consciousness, not to change the fate of the cosmos, but to bear witness to it. To stand in the cooling light and whisper back to the infinite, I saw you. I understood, and in that whisper, the universe is no longer alone. In the end, perhaps there is no real distinction between life and death, between the beginning and the end, between silence and song. They are all part of the same continuum, the great remembering that is being itself. Maybe the universe has already died, but we are still here, walking through its afterglow, living inside its memory and calling it time.